Ah, it's working now.
Guys, thanks for coming. So after a long time, again, we are the Science Application Association, non-profit association. I think no need to spend too much because I think today we are all friends here. Okay, so today's topic, thanks again for Peter. He will bring us the latest reinforcement introduction with basic idea how to set up an environment with clean and stable Baseline3. So let's get started. All right.
Cool. All right, first, can you guys see the slide? Yep, you should be able to see the slide. So yeah, today's topic is really just going to talk about basic of reinforcement learning. So the reason, the way that I started the journey, so-called the journey of learning reinforcement learning, to give you guys a bit of context, was that during my master research, I was focusing on an experiment based on verifying algorithms of some sort of smart battery systems. So my professors or my supervisors, he had a PhD student before him who was using some sort of dynamic programming algorithm to kind of determine what are the best sort of action in a home battery systems. So in Australia, where there's plenty of suns, a lot of people were installing solar panels on their roof. But the problem is that when the sun shines the brightest, most of the people is not in their home. So they're not using electricity. And when they come back in the afternoon, the sun has gone down. When they need to use electricity, their solar panel is no longer generating electricity. So it starting to become popular that people will install batteries, a giant battery in their home to store the excess solar in the morning and during the day, and then they can use it at night. And it seems like a great idea because, in Australia we also have a thing called off-peak pricing. So during certain hours, electricity is actually more expensive. So people can actually store the electricity that they use during the day from the solar panels in the battery, and they can actually use it in the afternoon when electricity is more expensive. Or in some state, they can actually sell the electricity back to the state. And you can see how this could be a complicated operation. When do you decide that you actually use the battery for your home? You can actually sell your electricity from the battery, export back to the grid. So that was the research that my supervisor, previous PhD student was doing, where he basically developed a way to project all the possible scenario, or as much as he could, and then use some sort of optimization to find the most cost-effective solution. And when I learned about reinforcement learning, I was thinking, well, this is actually a problem that you can train a model to adapt using this sort of method to maybe achieve similar results. So I get in the rabbit holes and all that. So a lot of the example that I use will get to do with solar panel and batteries and all of that. So that's where the context came from. But I'll get into it. So what is really reinforcement learning? So I'm gonna go through a couple of things. What are the key components, or what are the things you need to look out for? What makes up reinforcement learning? What are the advancements, or what are the algorithms that people are using? Challenges, not everything is perfect. There's no perfect solution for everything. And I guess I'll also give some so-called practical example. It's just stuff that I've been cranking up in the last 6 months after my Europe trip. So let's get into it. So really there's 3 paradigms got to do with machine learning in general. There's the supervised learning, so that's your classic, you label a bunch of pictures, cat and dog, and then the algorithms learn what pictures are either cats or dogs. So this is where you label all your data, and then you're trying to get your model to learn which label belong to what data when they see an example. So for example, pictures in the last the example I just gave. And unsupervised learning is when you have no labels, you just have a bunch of data, and you're trying to have the model to actually learn the clustering of the data. So I guess I don't really have a solid example for that. A lot of those would be actually categorization. So a lot of recommendation engines actually use this sort of method to derive their algorithm. So, they're trying to cluster what customer group, if they have this feature, do they belong in a group? And if they're in this group, should I give them recommendations? That's one of the use case for that. And finally, we have reinforcement learning, which hasn't seen a practical use up until very recently. And they're completely different to the last two that we talked about. The last two is really talking about can a model learn the difference between one data point to another through the various different methods. Whereas reinforcement learning is really trying to teach a model to produce some sort of decisions, and the way that you train this model is through giving a reward to the model based on a scenario. And the concept derives from the classic conditioning in animals. So in animal behavior, you guys might learn that when you give a dog a treat and you ring a bell, the dog will produce salivas because it associates the ring of the bell with a treat. It's similar to that. You're trying to, through the mechanism of providing reward based on a scenario, you're trying to have the model to actually produce the desired action in a given kind of conditions. And I'll get into that later. So that's kind of the three major kind of paradigms within artificial intelligence or machine learning. So that's the basic. So what is the key things that you need to know in reinforcement learning? That's the first thing is that you have an agent. So when I say agent, that's what I meant, is that the thing that decided what to do in a given scenario. So an agent is really, in this case, is the algorithm, or it could be anything. It could be a table. It could, you can write a bunch of if-else statement. That could be an agent. So really, it could also be a human. You can be a human, just deciding what to do based on the environment. So that's an agent, very self-explanatory. An environment is the thing, your program that your agent interacted. So an environment, it could be a video game, it could be anything, but it has to be a thing that has a set of parameters and something can interact with it. And actions and rewards are the things that kind of communicates between the agent and the environment. So the agent will produce an action. So the agent will decide what to do. That action, the environment will see what action the agent has produced. So in a video game, it could be your control. It could be left, right, up and down, all of that. And then the environment will feed back the agent based on the action it takes. So in a video game, let's say you move left, the environment can say, oh, now your character is in A position, now the next thing is in B position. So that will be the state that your agent is in. So that's produced by the environment. At the same time, it's also the reward. So if you have some sort of way to tell, hey, being in this environment is a good thing for the agent, the environment should produce and reward for the agent. And the states. So that kind of the four key components of reinforcement learning. So those are things that what constitutes, when you talk about reinforcement learning, those are the key things that you need to keep in mind. And you might think, what's the use for kind of, this sort of setup? What's the use for, having an agent, interact with the environment, produce a state and a reward? Wouldn't that just be playing a video game? And you'll be right. A lot of early research into reinforcement learning is actually just playing video games. Not that, playing video game was useful back in the day, but it was a very interesting problem for for computer scientists to work out, hey, what are the way can we, produce intelligent behaviors? The very early examples of, famous example, not early example, but famous example would be, AlphaGo, where they beat, the best human player in Go. Yes, that's the game. Back in the 90s, you have IBM, their supercomputer beating human in chess. And when people thought chess was like a unique kind of like human intelligence, only human intuition can play a game as complex as chess. But chess isn't actually that complex. I mean, it was complex for computer scientists back in the day because you have a lot of unique combinations. How would you produce a winning strategy based on all this combination? And when chess was beaten, human was like, oh, there are other things that you can. But turns out, humans are very good not only at playing video games, but also developing algorithms that can beat those things. And reinforcement learning will kind of like the focus of that. How can we come up with algorithms that achieve complicated tasks that we humans thought is only unique to us? And it's through very simple mechanism. And this pictures here is actually a example research that OpenAI did back before they did ChatGPTs. I can actually play a video of this. I don't know whether you guys have seen it. Can you guys hear the... Oh, it froze. I'll get this computer to play. Anyway, so here is I can share a couple of the screens. So here's, OpenAI back in, how long was this ago? This is 5 years ago. This is before they were doing ChatGPTs and all that, and they were, this example that they gave out, they were like, oh, given an environment, just like the one that you see here, can computer play hide and seek? Is that a thing that they can do? Would they just randomly wander in this environment and not do anything? So they basically have a very simple environment, and then they have agents. So you see the blue and the red thing, so they are the players in this case. They're trying to play hide and seek, very simple. And then they have obstacles in the way. Can the blue outrun the red? Can the red find the blue? So these are the questions that the researchers was looking through. And through their research, they're actually able to find that very complex behavior can actually be exhibited by these so-called agents after many iterations of trainings in this environment, and simply based on reinforcement learning. So if you're curious, I can't play the video right now because it's very laggy, but if you're curious, you can actually look it up. It's just called multi-agent hide and seek. And this was 5 years ago, before ChatGPT ever came out, and OpenAI was still cool and actually open about research that they do. And in fact, reinforcement learning comes into play very recently. So GPT-4, the so-called breakthrough model that OpenAI came out, rely on a version of reinforcement learning. They call reinforcement learning through human vectors, something like that, where they use human examples and they use some sort of reinforcement learning method to train the model to actually behave the way that humans want them to. So the ChatGPT that you use was actually trained through this method. DeepSeek had a so-called breakthrough in a recent method where they actually just have two models kind of talking to each other and then somehow reasoning. So when you use the current DeepSeek or ChatGPT version where they do some thinking and then produce a bunch of random crap and somehow arrive at the correct answer, that's an emerging behavior through reinforcement learning. It wasn't something that show up in the training data. They actually, the model themselves, produce this phenomenon. So these are the applications, and I guess the biggest things right now is in large language model. And you can also imagine robotic also can deploy this. So Tesla self-driving car, they talked about it a couple of years ago where they were using reinforcement learning to condition behavior in their car. So you can blame this when your Tesla crashes into someone else, which happened apparently too often. So let's talk about some of the key components. So I'll talk about the 4 key concepts that you need to know about, and I will dive a little bit deeper into them. So agents and environments are kind of the cornerstone. So without these 2, you wouldn't really have reinforcement learning. So agents are really, as I said, the algorithms that you need. So an agent needs to actually be able to understand the feedback that the environment produce, and they actually need to produce a set of coherent actions. And in the later kind of library that I showed you, some people already program all of that, so you can actually just use what they're provided, and you'll be able to, kind of create this scenario. And the environment is also important because the environment is what the agent interacting. So if you have a problem, like for example, playing a video games, like the slide shows here, the environment actually need to be able to produce coherent answers. So very often it could just be, your video game could be an environment, because a video game, what does it produce? It produces, based on the state, it actually gives out the screens. If you're talking about playing Ataris, it actually have pictures showing you what the state of the video game is in. It also produces a reward, like when you play a video game, you have a score. The score can itself be a reward. So, so that's really the explanation that you kind of need to know. Just think of it like a video game, but and actions and rewards. So that's also very important. So like, how do you define what an action is? So again, in video game, it's very clearly defined within the boundary of the game. Like, if you need to go left, up, and down, that could be your actions. But if you have some other problem, for example, for a while, people were talking about using reinforcement learning to trade stock. How would you trade stock? How would you go to the, how would you go on your, what are the trading stock app that you use? How would you decide it, what is the appropriate action that a model should use? Should it be buying 10,000 stocks? Should that be a valid action? Should that be selling the stock that you don't have? Should that be a valid action? So defining what an action is also important. In the early day when they're researching using video game, that's very good because video game, again, have a clear definition of what you can do within the video game. So that would be the actions. Is a thing too small for you guys to see, or like, can you make it bigger, or no? Anyway, so if you can't see, just sit further forward. And again, another thing is reward. Reward is actually the most important thing out of all of them, because reward define how it's the incentive. How do you incentivize your agent? So if you have some sort of desired outcomes, defining the rewards is extremely important. Having appropriate reward is extremely important because that would guide the algorithms to shape the agent to produce the output that you want. So again, video game, super great example because video game already have a clear defined goal, and the game designer already kind of, take those into consideration and, incentivize the human to do the appropriate action that they want them to do, and also get entertainment out of it. So again, if I use the example of stock trading, how would you define what an appropriate reward to be? Maybe earning money is a good reward to have. Losing money is a bad reward. And also you need to think about how often the reward comes up. Let's kind of go back to the slide here. So for example, if you have a video game that is as simple as this, right? And you have a grid and you want your agent, which is, maybe the car or the humans, they want to go towards a certain location. How would you define what are the rewards? Is maybe the distance towards the target location itself could be a reward. So, it's really up to you to decide what a reward could be, and there's no one single answer of what is the correct reward based on a certain scenario. But understanding how your agent will take in those rewards and produce desired output is extremely important. And the last one was just just repeating what I was saying.
Okay, so I think we have covered most of the points. So I think we can move on to the next slide. So this is 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 the next sl
So once you kind of defined, what are your reward, your environments, the next things would be how would you actually train the model to do that. And when we talk about training the model, we use the word policies. So the things that guide what the agent do itself is a policy. So your policy could be always go right, and the agent will just always go right. You can think of it as like a simple rules that dictate the agents and dictate how the agents learn. That would be the policy. And they're really two kind of like, doesn't matter what the policies that you choose, they're like kind of two classes of it. One is called deterministic policy, and one is called stochastic policy. So again, self-explanatory. Deterministic policy is just that for a given state, the agent is going to produce this reward. So no ambiguities. With stochastic policy is for given state, you might produce a probability distribution, and you can sample this probability distribution to determine what the policy is. So this is kind of what language model does. Language models sample probability distribution, and then they have some sort of like mechanism that determines like, what word do they say next. So they don't actually know when you give them a sentence like, this dog is, it doesn't always know that it doesn't always say this dog is wet. Maybe next time it might say this dog is blue, or something like that. So the library that everybody kind of use, and it's very beginner friendly, it's called Gymnasium. It started as an OpenAI kind of project. So the hide and seek agent that I showed you, that was apparently produced in when they used to be called OpenAI Gym, and they open sourced it. They don't want to deal with it, so they gave a bunch of volunteers some money, and they're like, okay, now like maintain this project for me. So now it become a open source project called Gymnasiums. So it kind of took all the things I was talking about. Really, it's a wrapper for producing states and rewards. It's a wrapper for producing an interface for your environment, and it has sort of like guideline of like what a state and a reward should be, and it also guide how it intake actions. And I can kind of show you what that looks like. I have make a very simple notebook. So all of this stuff that I showed you is on my GitHub. I also should change it to white instead of, oh wow, that is so blurry. Color filters. That's better, I guess. I can also change the resolution. So, actually, I should. So before I showed you how to make your own model, make your own environment, I should show you how to use. So you can't really see that over here. I can actually just go on the OpenAI Gym. You can see they still maintain their own version, but it's already called Gymnasium now. Gymnasium. So here's the GitHub page. Maybe I should change it to live theme as well. How do I do that in GitHub? Super hard to see. There you go, that's their documentation website. I wonder, do they have live theme? can see better. So it's actually super easy to use. They also have some sort of like built-in environment. So for example, this like, things that playing is actually a lunar lander simulation. And the goal, and obviously the spacecraft is your agent, and you want to land in between this pole, and you can train your algorithm to do that. And they have a Python kind of like libraries for you, an API for you to use. And it's super simple. You just import the library. And if it's one of the built-in environment, you can just go gym.make. They have a bunch of video game version. They have the walking stick that you see, the really ugly one. The lunar lander is one of them. And you can just go environment is equal to gym.make. So you make your environment. And to sample the environment, well, first of all, you need to initiate the environment, so you need to reset. And every time you do an action, it should produce an observation, as it does here. So that would be the state that I talked about. And you can just look through it. You can just go like, you can just randomly sample them. So they provide an API for you, or function for you to just randomly sample the action. So you don't actually need to build an agent. You can just tell the environment, hey, what is a random but also appropriate action or valid action to take within this environment? It will produce that. And you can feed the action back into the environment using end.step. And then it will produce all the things that you need to know, the observation, the reward, whether the environment has stopped or not, so the terminated and other information. And if it has terminated, you can just go end. They also have a render mode. So for example, this video game, if you wanted to show what's happening, because you don't actually need to display something, they have a render mode that shows pictures for all of that. Here's the documentation, but here's just like examples of how to use it. So it's like actually super straightforward. But if you have, as I said, like a custom problem that you want to solve, if you have a custom problem that you want to solve that is not built into the gym environment, it's very straightforward. You can just build your own class, and you need to, in Python, and you need to inherit it. It's called gym.inf, so you just inherit the class. And there's 4 key kind of like method within the class that you need to make. So you have int, so when you first started, what are the parameters? Reset, so when you initiate an environment, what is the initial condition for that environment? So you need to make an int. If there's some randomness to it, so you also should take in a seed and all that, other options. And then another things I showed was steps, so you need to program in how the environments update the internal states based on given actions. And if you need to render, you also need to write a render function. So, as I was saying before, I was viewing this kind of problem in the lens of the battery solar panel systems. So, if I want to initiate, I can actually just start this could be a very simple kind of like battery management systems. This environment could be simulating a battery and management systems. And so when I initiate, I need to actually define some sort of parameters. So I need some sort of things. So for example, maximum capacity for the batteries, what are the charge rates. You also need to define an action space. So this is a must, so it kind of defines like what are the valid action you need to take. And they have a class within this environment, within this library called space.box. And it's kind of just defined like, if you have a continuous space. So in my case, there's only one single kind of parameters with my action, which is the charge rate. So how much can I charge? And it could be maximum, and it should be bound between -1 and 1, and it's in continuous. So you can define all of that here. So what are the lower bound is -1, the upper bound is 1. It's a shape of 1, so that defines kind of the matrix. So it only have 1 parameters. And the type is a float. You can also have discrete action. So you can see all of that in the documentation. And also the observation space. What does the reward look like? What are the, it's often produced, it has to be a matrix. So it also only have one state, so which is the battery charging state. It has lower bound is no battery, so 0. Upper bound is 1. It also has shape of 1, so because there's only one parameters for that. And you see very often we actually like to normalize all of this. So for example, you can actually make the lower bound, or if your battery is 0 and the upper bound 100 because it indicates 100% of the battery. Or it could be the actual energy. How much energy do you have? Like what's the kilowatt hours? You can actually put that in. But if anyone have done, machine learning, they really don't like having, the shape everywhere. Like, they really like to normalize kind of their operation. So you often see that the lower bound and the upper bound are just -1 and 1. You define some sort of arbitrary kind of like, limits. And if you have some sort of real value associated with them, you can actually map them and do that within the environment. But that's sort of like the things that I find. You also need to initialize some states, so what are the battery level, the current step, like if you, for example, so I might have a discrete step with interacting my battery every 10 minutes is one step. You can see like my maximum step is 24, so my one step is 1 hour. So I can actually run this. In my environment, if I have unable to connect. God damn it. Sorry, run into. Another thing is that like I have all of this running in a container, in a Docker file container. So if you want to use it, you don't actually need to install anything other than Dockers, and you just run the Docker files. It will spin up a labbook environment, and you can just run the labbook environment in it. Don't mind what I'm doing here. I'm just trying to find the stupid link. Here's the link. So yeah, like it will open a Jupyter Notebook environment, and you can use. If you don't know how to use it, that'll be outside the scope of this session. But I'm just trying to get it running. Yes. God damn it. I'll run it next. I'll just keep going with it because you don't really need to see. It doesn't do anything just yet. So once you initialize the conditions, the next things you got to do is to actually tell the environment what to do when it first started. So that's what the reset function is for. So it's just straightforward. When it reset, it starts in a random condition. So the battery could be anywhere between 20% and 80%. The current, you need to set the current step to be 0 because it's just start of the day. And then you produce the observations. You tell them what the observation is. You actually make the observation that I was just talking about, the bounding boxes. So you actually have to like update your observation and then you return it. Super straightforward. Once you do that, you need to think about, okay, like how does my thing update the internal state when I see an action? So that's where the step function comes in. The step function accepts an action. An action is often a matrix that just give it to them, so you actually need to read. So as I said before, in this case, my action is just one single parameter, so just what are the charging for this battery is, how much I would like to charge within this param. So I'll just take in the action, read the first state, and then multiply by the maximum charge rate because I normalize it between -1 and 1. So -1 is discharge, all of it. And and one that will be charged all of it based on the maximum charge rate. So I just have that multiplied by the maximum charge rate. And I need to see what my level is. So this is really just doing calculation. You're updating the internal state of all of that. And then you actually need to think about how do you calculate my reward. This is just an arbitrary examples. But yeah, like at the start, the reward is nothing, or like for this step, first of all, they don't have any reward. And then I just go like, well, I want to penalize them if there is a waste action. So for example, the battery is already full and I'm still trying to charge it. I'll go like, well, no, you shouldn't be doing that, and I give them a penalty. So the penalty will just be the waste energy multiplied by 5. Very arbitrary. But, and if it's not, having waste energy, I'll go like, okay, well, I'll take the percentage of the action they're doing and give them a little bit of reward. So I'll, again, very arbitrary, I'll just doing that. Anything else, maybe just doing some random action, I deduct 0.1 score out of it. Again, this is a random example that I give, so the reward doesn't actually mean anything. I'm just kind of stepping through like what the logic would be if you build your own. And the next thing is that you need to update your observation and return it. So you actually need to, provide what are the states. You also need to count, because I said like there's only 24 hours in this simulation, so I actually need to update what step this is in. And has it terminated? If it hasn't terminated, I return false. So again, these are the things that you need to define. So for example, if the step is more than the maximum step, I return truncated or terminated. You can also, there's an info, so there's a tick. So if you have more diagnostic that you want the environment returned, but you don't want it to be part of the state, that could be a thing. And you put it in you throw it in the info. So it's good for debugging and also, for you to understanding what's going on. And then you return all of it. It has to be in this format, so that need to be 5 things. So you need to have an observation, a reward, a truncate, and a terminator, and an info. So that's what a step function do. And again, if you want to use it, it's super straightforward. You just create it. So I created an inf based on my class. I initialize it. If I want to use it, I need to reset. And again, as I said, if you haven't built an agent, you just want to see the environment in action, you can randomly sample an action. So that's what the action space.sample function is for. It produces a random action. And you can just fit it back in. So you go nth.step, right, like put in the action as your argument, and it'll return all the stuff. You can print it out. So that's how you would use it. Because I haven't set up the Jupyter notebook, I'll set it up later when I actually need to run some concrete examples, and I'll not bother with running with it. But yeah, that's how you would build an environment if you are thinking of like, you have some problems, you want to use, reinforcement learning to tackle that. This is one way to do it. So now that I talk about kind of the basic, like how does the algorithm actually learn? And there are like various algorithms associated with, the realm of reinforcement learning. The one that I'm going to focus in is called model-free reinforcement learning. There's also a model-based reinforcement learning. That's a lot more complicated and it's not very used. So I'm just really going to focus in model-free reinforcement learning. That itself is already quite a handful. So, when you think about reinforcement learning, one of the things that, when people initially tackle it, how would you associate, the reward based on the action? The first, I wouldn't say the first method, but the method that the most intuitive would be value-based method is when you look at a certain state. For example, we go back to our very simple video games here. Just a grid. Each kind of position that this little creature is in, that itself could be a state. This is a very discrete one. And I can go like, well, each block I could assign a value to it. And for example, going to the lake is, they can't swim in the lake, so I can associate -100 with this state over here. And I can go, well, when I'm here, going right, that state will be -100. And going down is a survivable state, so I can assign a value of 10 over there. So that would be the concept behind value-based learning. And because this is machine learning, you're not going to hand assign value over there. The people will be like, well, why not come up with an algorithm that will actually learn kind of like what state are the values in. So the very simple one would be I have a table and I actually have the randomly sampled environment for a while, and I can use some sort of like backward propagation or whatever statistic kind of like function to, once you like walk around the environment a bunch of times, you learn the state and you store them in a table. So that's what a Q-learning algorithm is. It's really just like you sample the environment a bunch of times, and over time you kind of like, based on what rewards you get, you assign a value to that given state. And then once your agents arrive in that state, how do you decide what action to take? You look at your tables and go like, I pick the one with the most value into it. That will be your Q-learning algorithms. This is like very primitive but also effective, depends on what you are doing. And after a while, people will be like, well, that's fine if my state is only a 16 by 16 grid video games, but what if it's getting much, much, much bigger? And I can no longer, the state action table for my Q-learning algorithm is maybe like 1,000,000 row, for example. That would be, super difficult, because think about it, like each state, you have your state, and each state you can have possible actions. So your table will have a state and an action, and then you go like, okay, for this state, for this action, I have these values. So if your state and action is super complicated, or if it's continuous, it will be impossible for this method. And people are like, why don't we use a like neural network to associate itself, like learning a table, I have a neural net. And for a given state, I'll put it into a neural net, and it will produce, a bunch of values for a given action for me. And your policy, as I was talking about, like what are the policies? The policies, what dictate the agent to do. In this case, your policy is always choose the best value. So policy is super straightforward. You just, in this state, you pick the action which have the most value to you. So so-called greedy algorithm would be that. But yeah, this is value-based, and it worked for, as I said, if you have a very simple, straightforward, for example, a chess game can actually, be done with this method. You can have the agent to look, play chess randomly, and over time you will actually build up, for this state. If I choose the rook to move forward, that will be an action. You will actually learn a value. What are the reward for that? If you program your reward function properly. So that would be one way of doing it. I kind of skip over how I talk about learning. How would you actually learn? There's actually an algorithm. There's various algorithms behind this method. I'm just talking about like, how would you, what are the end goal for learning? How would you learn? That itself, is a whole can of worms. So I kind of hinted at, so a lot of time is actually just exploring. You just, at the start, you explore, you randomly have or for example, you initialize your random value tables. And then, you know, when you tell the agent to do something, you just like pick the best value. But at the start, the value is random, so just pick whatever value. It might not be the best value. And, you know, and then after you've taken the action, you look at the rewards. What are the rewards for you know, the state that you've given it? And, you know, the reward might not match up with the value tables that you have or the neural network. And then you actually use the difference to update, you know, your reward table. There's a bunch of ways to do it, but that would be kind of like the overall way to do it. At the start, you randomly initialize your policies, or not your policy, your Q values tables or your Q neural network, and then you have the agent to just, based on this value network or table, do the stuff, and then you do it a bunch of time, and you actually record, like, okay, what are the rewards that it has done, and then you use back propagation or whatever way that you have, and then you, based on the reward, you update it, have it do it again and again and again and again and again, and eventually your value table or your value network will actually match up with, you know, the reward that you have. So really, that is machine learning. You don't actually program in what to do, you just set the rule. So right now the rule is that I have a way to tell you what value is, go and try it out. If it doesn't match up, update your value table based on, you know, what you have given. Try it again until, you know, your value match up with the reward. So that would be the learning algorithm. You can think of it as like, you know, you use back propagation. You can use back propagation for this too. But the loss would be, if you use back propagation to learn, the loss would be you explore it, you sample your reward. The difference between the reward and your value would be a loss. And you'll be like, okay, minimize the loss, match your values based on the reward. So that would be one way of learning. There's another way, but that's the most popular one. So that's value-based learning. And another one is called policy-based learning. So instead of actually learning a value based on a state and an action, and then pick the best value, I skip that step. I just told the policy, it's like, hey, now your job is to give me the best reward, or give me the action that would eventually give me the best reward. Sounds super arbitrary, but you know, in machine learning, it's all about efficiency. So for example, the previous example I gave you, you learn a value first, and you go like, okay, the value should be, you know, for given state, the best action is the one give me the most value. And what is the most value? The most value is what eventually lead to the most reward. And there's a lot of steps your algorithm need to actually learn. Okay, best reward associated with best value, and then I program it, sample the best value to give me the best actions. Instead of doing that, I just skip that. So that's what policy-based kind of method is about, is that instead of arbitrarily defining a value that match with the reward, I just go nuts, but eventually I want you to give me the best reward. So you can think of it instead of like, you know, I'll talk about that later. And this works if your observation is super complicated. So in here, you know, in a Q table environment, you need to be a discrete kind of action space. So if my action space continues, the Q learning will no longer work because I can't possibly have every single continuous values map it down into a table. So imagine if I'm playing an Atari game, or this one over here, an Atari game. The observation is actually just a screenshot of the Atari game. You know, I would not be it would be impossible for me to program a table to kind of learn like, okay, this screens here is it's one observation. You know, how would you distinguish, like, you know, guess that's where the deep Q learning comes from, because you can actually use a neural network and produce a value for you. So your neural network could be a convolution network that look at the screens and okay, like I now understand the state. And this picture give like I think for this picture, this action give me various values. But what if your action space is also continuous? So value-based method really only work if you have either discrete state space, or if you don't have a discrete state space, a discrete action space. And if your action space is continuous, you can't really associate every continuous action with A values, right? So that would be very difficult. That's where policy-based method comes from. And in fact, some algorithm actually take in a hybrid approach. They will, adapt like some sort of like value function within, when they optimize their policy functions. So that would be one approach to it. But the big thing about policy methods is that, think about the previous example I told you, a value-based method, you need to have some way for your value function or your value, the things that you talk about values, to actually learn the values, right? In here, you just straight up go like, I don't have that. I'm just gonna have my policy. It could just be a neural network, and I optimize it based on a given state. So that would be what a value-based function is. And really, it's just a bunch of maths. You will actually have your math. So this is kind of like the equation that you would kind of like implement if you want to program in a value, like a policy method algorithms. And it's really just, you look at, your bunch of, the key thing is that like each action, you should look at what each action is. You look at what could be the possible reward. You look at the log of that reward, and you trying to summarize all the possible action and all their possible reward, and you want to maximize that function. Super complicated. There's a bunch of math behind it. I leave a link here. So Hugging Face actually have a course talking about that. Really, but what this is doing is that you want your neural network to actually learn for a given state what is the best action. Very arbitrary, but that is really essentially what it's doing. And it's super great for high-dimensional space, because now instead of talking about discrete values, what each action or what each state give you the best values, you really just sampling, your neural net, and then for a given state, it should produce a action based on this function over here, the policy gradient. You can think of it as like back propagation. In back propagation, you have your action against your loss, and you want to minimize your action against, or your output against the loss. If anyone here familiar with back propagation?
Gradient descent upward.
Yeah, so really you kind of mapped out like, your loss function space against kind of like your parameters, and then you want to go down in your gradients. Policy gradient is exactly like that, except you do the opposite. You want your parameter space against your reward space, and you want your parameter space to produce more reward. So you're really updating your parameters based on, the reward you sample, and you go like, if once you find out the gradients of that, you increase the parameters that will give me more reward. So you can think of it as back propagation and gradient descent. You do the opposite of that. Instead of having a loss, you have a reward, and you want more reward. That's really it. If you're interested in the math, go to this link over here. It's on Hugging Face, or you can just type Hugging Face deep RL course. They have a whole course. In fact, a lot of my slides here, I just took it out, like a lot of the pictures here, I just took it out of their slides. Now, if you think all that is complicated, it fucking is. No one's going to have time to implement that. So really, that's what Stable Baseline3 comes from. It's a library that some guy have rolled up. I'm pretty sure it's one dude. It started with one dude, now it's a team of dudes and gals, I guess. Where they implement all of that for you, and you don't have to like hand implement your own algorithms. And in fact, based on all of this that I talk about, policy gradient is actually extremely inefficient. If you follow kind of these math equations, very often you don't get, you can train a bajillion epochs and you won't go anywhere because sometimes your reward can be super sparse or your reward space is, highly stochastic. So your gradients would actually go haywire and you can't really, step towards the maximum gradient that you want. There's all sort of optimization based on this. So there's one called the most kind of talked about as PPO, so proximity policy optimization. So instead of taking the actual gradient, you have some sort of approximations of the gradient or approximation of the log function that build a gradient. DeepSeek, so DeepSeek has GPRO, so it's group policy relative optimization. So where they, instead of taking this, they actually have some way to sample the log. Instead of they sample the actual log, they sample a bunch of average of the log. Super complicated, but all the derivation is based on policy gradients, and they want to optimize, and the efficiency of this method. And again, you don't have to hand implement. If you hand implement it, you'll be doing a PhD in it. But some dude already kind of implements all of that in Stable Baseline, and I can again show you how that works. I want to save, what the hell? Oh shit, that close. Oh, so here, speaking of before, so here is the sample environment that I built. So based on the actual problem that I was talking about, it's the one that I do my master research based on. I actually build a environment based on a more realistic kind of like system in a home solar battery operation. So this is the environment that you can see. I can kind of just show you. Very similar to the one that I had, except it just have a lot more parameters. So I took kind of like a bunch of like datas from Ausgrid, so they're the Australian Grid Association, I think, and they have like a bunch of sample data that you can use to look at like, what are the different things. And I use those data to kind of build like a simulated environment in a battery solution. And you can kind of just see a lot of that is similar to what the example that I showed you, but a lot more complicated. I have, my actual battery capacities as my parameters. And I need to have a data frame to log all the example data that I downloaded and use that to simulate it. I also have. Anyway, if anyone is interested, you can have a look. I also have a way to kind of not simulate, but to calculate what the battery degradation is. So the really concerning things that my supervisors was looking into was battery degradation. That was one of his PhD students' previous research as well, so I implemented that over here. It's just a bunch of equations and all that, and this calculate kind of like what are the degradation, and I implemented over, and the degradation, I used that as part of my reward, so each degradation, so I kind of want my agent to also make me the most money when I sell electricity based on the grid by charging a lot of batteries, but at the same time I also wanted to consider like, you know, what are the degradation, because each time you charge your batteries, the battery degrade. So there's a trade-off from you know, soaking up the sun and charging your batteries versus like, you know, the value that it lost based on the degradation. Also, I also write like the entire kind of agent class. So I talk about agents, so how would you interact with it? I actually write an entire class method to kind of just allow me to easily deploy algorithms to do that. I also have handwritten rule-based algorithms in it. Anyway, so that was extra detail from the last slide. So if you want to look at how stable baseline is used, stable baselines kind of write the entire thing based on gymnasiums, so they work well with gymnasiums. So to use stable baseline, you need to have a kind of like gym environment going on. So this is the gym environment that I built beforehand, and you need to kind of make a function that will return the class that gives you the gym environment. So I have the, you know, this is some utility function. And stable baselines, because you actually, as I was talking about before, you actually need to like run this environment a lot of times. So you actually need to parallelize kind of your operation. So stable baseline comes with a class that can factorize the gym environment that you have. So the gym, because the gym environment is based on kind of like a Python API, it's just like a single thread operation. So if you want to run it a bunch of times, super inefficient to use this for loop. So stable baseline have a factorized way to do it. This is kind of like how they do it. So, you know, so you kind of need to like make a list of the function that will return the gym environment, and you pass it through this dummy vec.env things, and then it will vectorize it for you. And in fact, stable baseline wouldn't work if you just give them a gym environment. You actually need to vectorize it. And how do you use it? Super straightforward. Stable baseline already have all the algorithm implemented. So if you want to use PPO learning algorithm, you just import PPO and you make a model called PPO, and then you kind of like throw in all the parameters, appropriate parameters, policy, so MLP, so it's just multi-layer perceptrons policy. So that's kind of like the standard because it uses a neural network. I think there's other policy and never used them before because they wouldn't be as good as this one. You need to pass the environment into it. Verbose is just one of the things that you use. And the learning rate, so again, like think of this as like a back propagation problem, but instead of like you descend down your gradient, you want to ascend in your gradient. So you need to give them your learning weight, your gamma, so your gamma is kind of like which one is gamma? I can't really remember. But yeah, you can kind of explore that. And also because it is a factorized operation, so you can have your batch size, you just give them your batch size. This is very similar to kind of what you would do if you're doing a back propagation. So that would be your model, and straight up just model.learn, and you will run that learning algorithm for 50,000 times. What it really means is that it will just, use these algorithms to sample the environment, or it will run this in simulate the environment 50,000 times, and it will give you the results. Often, longer is not better. So you kind of have to explore it. So obviously short, if you only run it 10 times, it wouldn't really learn anything. But if you run it too long, it might actually go kind of overfit for specific algorithm or like a specific observation that it has learned. Because it might stumble, for example, like early on it might stumble that, in this case, if I always turn right, or whatever the case is, I get a specific reward. It might learn that, and it might overfit for like a specific kind of like conditions. So again, there's like a trade-off, and it's something that you can, explore yourself. And obviously, stable baseline also give a evaluation function. So how would you know that your agent has learned well given this policy? You can just evaluate it, and it'll actually give you a mean reward. So like how much reward has been produced based on this test evaluation. So we'll run this environment back to front 5 times. So that's what the number of evaluation episode means. It's deterministic as well. So it wouldn't yeah, so again, all those complicated crap, super straightforward. Stable baseline have, whether it's value-based or it's policy-based or it's a hybrid kind of learning algorithm, stable baseline have a lot of that implemented already. Do I want to plot this? I probably don't, because learning this takes a long time. Stable baseline do have GPU acceleration implemented, but not all algorithms can work with GPUs. A lot of them are still kind of CPU based. For example, if you're using a value-based learning and it's not like a super complicated one, they might not work with GPUs. So again, I think the stable baseline kind of documentation explain all of that. And also the Hugging Face page, they talk about a lot of the key kind of algorithms. So if you really want to learn the inner working of that, you can go through that. And I got to say, some environment works better for a specific learning algorithm, or the way that you program your reward works really well with a specific learning algorithms. But if you have your own problem, so for example, it's like I have kind of my problem over here I programmed, the reward is a lot more important than the learning algorithms. If you program your reward right correctly, and you think your rewards will give you the optimal result, the learning algorithm is really just give you a more efficient way to arrive to that result. Some algorithms never give you the result, so that could be a problem with the algorithm, or it could be with the reward. You never know. So those are the things you kind of have to explore on your own. And so all the stuff that we were talking about, those are called on-policy learning. So it's really, all of this is that you need to actually interact with the environment a bunch of times, and then you update, your values or, your policy given, the rewards. So these are called on-policy because you actually interact with the environment and you use that reward straight away from the environment to give you, and you update your policy based on that. And there's a way called, and it's actually super inefficient. And people were like, how can we do it better? Because supervised learning and unsupervised learning is extremely efficient. There's already so much algorithm and acceleration implemented for those algorithms. Why? Because they have the data on hand already. Supervised learning and unsupervised learning is really just, you take all your data and you pass it through your learning algorithms, and that's it. So really the bottleneck is how fast you can pass your data between data and algorithms. Whereas based on all of the policy, online learning, algorithms I talk about, you actually need to sample your environment. You actually need to interact with your environment. So if your environment itself is super inefficient, maybe you need to do a bunch of calculation to arrive in your reward, or it's a video games. You actually need to rent the whole goddamn video games. You actually need to play the video games to give you the reward. It's super time consuming. So people were like, why don't we just actually record all the interaction we have with this environment, store them as data, and then process them afterward. That's what offline reinforcement learning is. You don't actually sample your data or sample your reward live. You actually just have a bunch of data of those interactions, and then you use maybe a supervised or unsupervised learning way to actually kind of like learn the behaviors. I think Tesla was like the one that kind of pioneered this concept, because when they were developing their full self-driving, hasn't full self-drive yet, but when they were doing their self-driving kind of way, they can't actually test out their car in real life. When they test their algorithm and they crash, and they were like, oh, that's negative 10,000 reward. You already crashed the goddamn car. It's super expensive to actually run online policy. Or you might use simulations, but the things are like simulation takes a lot to learn. So they kind of pioneers. All their cars have cameras, looking through them, and they also record all their drivers' actions. So they actually pop all those data and they feed that through their offline learning. Use that to kind of like pre-trained their model first before they actually use that as their online learning. So it's also kind of similar to how current language model learns. Current language model, you pre-train them. Really, you just throw the entire internet at them, and then have it as like a autocomplete, train it as an autocomplete models. And then once you train it a bunch of time, the model kind of learn all the knowledge and all the kind of behavior as a text, and then you later fine-tune it using other method and eventually reinforcement learning. Because you don't want to start as as a random kind of agent and just have it wander in the environment. Because if you do action randomly, you're never going to go anywhere. So that is actually a lot of the downside of reinforcement learning, is that you very often don't actually produce usable agent, because a lot of the time your action just don't produce good reward. Maybe you can run an entire episode of the thing just crashing and not giving you good reward, and by chance, by luck, you produce a good reward and then the agent learned that. So to improve efficiency, this is like the method that people come up with. It's called offline reinforcement learning. And one of the approach is called decision transformer. It's relatively recent, because people are like, well, transformer is such a good kind of sequence-to-sequence predictor. Why can't we model reinforcement learning as a sequence-to-sequence problems? So what they really do is basically what I was doing over here before, as I was talking about. They took a bunch of reinforcement learning, or the simulated environment interaction that you would use to train a reinforcement learning model. So instead of training it live, you just have it sample a bunch of time. And then you hope that based on all those random kind of data that you collected, there will be something useful in it. And they basically use a transformer model to predict kind of what are the next state, what are the next action, and what are the next reward. It might sound like the shit that I was just talking about before, and in essence it is, but the approach is different. And this method is really bridging kind of all the advancement, all the efficiency that supervised learning already produced with reinforcement learning. And I also happen to implement that. Oh my god, that close again? What the hell happened? So if you guys go on my GitHub page and look at the README, I actually already have like all of the stuff that I talk about. You can actually just run them with the environment that I built. And I also built basically mini ChatGPT models to run that. And I also have built I also built a kind of like a sampling kind of like function that just sample a bunch of like, interaction based on, all the previous like algorithm we just talked about and run it. You can check it out in here. And I figured out running it would actually takes a long time even with the GPU that I have. So if you look at it, we go all the way back to stuff. So yeah, this is how you would, maybe I should actually just go on my GitHub page to read me over there would be better. How do I change GitHub to not be dark mode since setting has been setting? Appearance. Yes. Light default. There you go. So yeah, here is kind of the page. Really, you need to go down to usage. So here I have a program. So if you want to use the environment that I built, you kind of need to download the data. I have write a couple of like helper function to transform the data into the format that I need that fit into my environment, and then I initialize my environments based on the data set that I have. Also make an agent that uses a rule-based algorithm, so no reward, none of those. It's just rule-based, so it's really just like charge the battery when it's like lower than 10% and discharge the battery when it's like higher than like 90% and all that. And I also wrote a kind of sampling and method based on in my agent class, so you can just run the episodes and the agent will just like run it all based on this environment over here. And then to create all those like data that I was just talking about to use for offline reinforcement learning, I also wrote another function which basically run the simulation I just talked about in parallel and log all of the interactions and store them in a kind of like data frames. And all of this is just how to use the agent class that I wrote. So this is like custom stuff that I built just to make it easier. And here's another way of like showing how to use the trainer method. I also wrote a trainer method, so instead of all the boilerplate code that I wrote before, like straight up just like, I can train all the stable baseline models. So there's like 5 different ones that I choose. I just train them. And I also sample kind of like all their interaction during the training and after the evaluation to use that to train my transformer. And so this is how I use my kind of like transformer. So I have to first load all the like interaction that I just stored into a trajectory data set. Again, another custom kind of like data set class that I wrote. It's pretty, and I also have to build a transformer model. I can show you guys later how the transformer model is run. But it's basically a miniature version of ChatGPT in a way. And then yeah, and again, I wrote another trainer method to just train kind of like, you know, my transformer to run off all the data that I just used. And then it's basically just how I copy this code from the mini ChatGPT someone wrote. It's like, how do you train your own ChatGPT in like a super straightforward way. And all of that is in here. We can first look at what the transformer model looks like. The transformer model kind of consists, if you look at, you know, if you go look at DeepSeek, I think DeepSeek have a very similar kind of like PyTorch version for their DeepSeek model. It looks similar to this, but a lot more complex. So first of all, I have the attention mechanisms. And the attention mechanism just consists of, you know, your QK and V, so your kind of like your attention things.
This is a complicated concept, attention mechanism.
If you guys have like kind of like understanding of what the like attention mechanism looks like, this is like copy and paste of that. But yeah, so I have my attention, this is my attention layer in, you know, your ChatGPT, and then I have it to calculate the attention in this particular way. Then this copy straight from that, and you know, I have my attention layers. And then I string those attention layers into a block, so I need to have my attention, I need to have my normalizations, and I have to have my feed-forward kind of like layers. And then once I have that, that's one attention block that I have. And then really a transformer is just the attention block in parallel and in series. So they have a bunch of attention block in parallels. They will, you know, pass all of your kind of like tokenized tokens into all those blocks, and they split out a bunch of stuff, and then they have another attention layers in parallel and do all of that. They do that a bunch of times, and ultimately they have a kind of like decoder, so they have a way to like kind of unpack all your attention kind of like tokens into what you want to sample eventually. Not going to get into that, but yeah, that's what the attention kind of like model looks like. And to train it, I kind of just wrote a kind of data set. So if you want to train your own kind of transformers, these are like in this setup, you kind of really have to write your own kind of like data sets class to feed all the like you need to take all your data in appropriate ways and then like, you know, give them to your transformers. So really, this just loop all the. I store them in a polar data frame. This basically just read that and return the polar data frames in appropriate formats. Another thing I kind of skip forward, but important, is that you need to consider what's your reward to goal functions. So that's something that I kind of skipped before. So when you were in a state, so let's say you haven't arrived at your ultimate end state yet, and this is kind of like estimate what are the rewards down 10 steps to the state. So when you run your kind of like agents, you don't want it to just learn the reward, because a lot of times, as I said, there's no reward for this particular state and for all the action they can take. What you want to incentivize to them is to calculate, okay, if I take this reward, and now also the possible next reward, the next reward, the next reward, you want to add them all up together. And the furthest rewards will, you know, I will kind of deduct them and kind of like discount them. So really what this is doing is trying to incentivize, you know, your agent to like not only look at the immediate rewards that you have, but also the future rewards. But it kind of comes in naturally with the way that the transformer model works, because, you know, in the rewards. So when a transformer, it produces the next tokens. Right. So for example, the pictures here. What the fuck? So really, this pictures is like you can think of it like this. This is how they model it. I have all my action, my state, and my reward. I just throw them into the transformers, and then have the transformers to tell me for all of this previous state, action, and reward, as well as my current reward or the next reward that I want to have, predict the state, action, and reward for me. And you don't actually, have it to calculate the actual reward. You have it to calculate the reward to go. But yeah, that's what this is doing. And you also need to write your get items, because once you have a data set, you need to pass it into a data loader. And your get item is how you tell the get loader to load all the data. I implemented a sliding windows here because it's not possible for me to feed the entire episode into the transformers. You actually need to, for a specific data set, you actually need to give them a bunch of random windows or the context windows that you have within that whole data set. This would be somewhat similar if you are trying to train your own language model from scratch. You would probably also need to write a dataset class for all the text that you have. If you're doing it from scratch. And then in the training function, it's just really your simple kind of trainer. What you really need to do is that you need to initialize my model. I need to do my data loader, as I was saying before. I need to pass my model to the GPU, and then and I just look through how many epochs I want to run. So epochs, how many complete set of the run through your data sets you're doing. And then, and you just sample it from your data loader. And then for each batch that I have, I run it through and I, do my typical optimized. So this is like a boilerplate, PyTorch training code. I'll sample it. I calculate my loss functions, and then I update it using the my scalar.updates. There you go. Anyway, so that's kind of the gist of it. And I kind of, that must have crashed. And if you go through my GitHub, I actually have a library, or not a library, a notebook that already kind of go through the whole run, all the steps that you need to sample it, train it in stable baselines, train it in sample the stable baseline agents or all the PPO and all whatever, store them in a data set, and then run them through the transformers in the test run.py notebook. So it's kind of all over here. You can see a lot of them are just model.learn, super kind of straightforward once you have the algorithm for it. And I've run all of that except for the evaluation function. I actually need to evaluate how effective my algorithm is from that. That's something that I haven't done. Maybe I've done all of this for nothing. After all of that, a simple rule-based algorithm might be more effective than running all of that. I didn't know yet, so that's that. But yeah, that's kind of the demo code, kind of the example code for that. So what are the challenges you would face in reinforcement learning? I kind of hinted a little bit of that at the start. So when your model learn, you wanted to, at the start, you wanted to actually see, just think of it when you play video games. When you first start playing Minecraft, for example, how the hell would you know how to play Minecraft? You don't. You just go around and try a bunch of different things and see like, what happens. After a while, you don't want to keep just randomly doing shit in Minecraft anymore. You actually want to do something. Like, what is there to do in Minecraft? I don't know, but you can slay a dragon, you can build a village, whatever. But eventually, you want to start doing appropriate actions. And a lot of the learning algorithms that I mentioned beforehand, they kind of have to balance that. You know, at the start, they need to do a lot of explorations. They want to just keep like exploring, like, you know, what are the possible states, what are the possible rewards for this state and action. But after a while, you want them to actually hone in, to actually like start the updating, you know, you want to start updating the rewards. You know, the reward signal that you're given, you want to reinforce that. So like that is a tricky thing to kind of balance. And from most of the paper that I read, you really need to dig through, you know, the reward. You want to see how your reward shows, and you, for given environment and a reward, you want to see like, you know, you want to pick a point where, an inflection point where like, you know, you no longer explore, you no longer want to keep doing random action. You want to kind of like start like doing the stuff that gives you more reward. And language model runs into this. Language model, you can imagine, is like a gazillion times more complex, because what is a good reward? Eventually it comes back down to like, how do you reward the model and how do you pick up reward signal from that model? Yeah, and this is kind of what I was talking about before. How do you produce appropriate reward? How do you what is a good reward function? Because a good reward function, actually, after training, you want your model to actually produce things that you want. So you want to give it a breadcrumbs, like, you know, here and there, so the things that you wanted to do, you give it a lot of good reward. But another thing is a sparse reward. So maybe a lot of the time the model just don't actually have any rewards. Maybe they may be doing something useful towards a reward, but you might implement your reward function in such a way that doesn't give them the reward. So you might actually want to, in the reward function, say, hey, like, you know, some of the action that you knew for sure is good for the model, you actually want to give it the reward. But at the same time, you don't want it to be too controlling. You don't want to like, because you actually want the model to like produce intelligent behaviors that goes towards that reward. And if you like hand lead them to that ultimate goal, it's not really learning. It's just them optimizing your reward function. Yeah, so writing the reward function is super important and a great deal of research into reinforcement learning. And another one was scalability. So how do you scale reinforcement learning? And really this comes down to, again, training. So, and that's kind of what offline reinforcement learning is trying to tackle, is that like, you can only run so many simulations. You only have so much compute into running simulation. And a lot of this simulation could just be the model failing and not getting the reward that you want. And how do you scale that? And, you know, if you're a Meta, you might have shit tons of money and you just, you know, pay this guy $1 billion and pay the other dude $1 billion and spend like $100 billion buying GPU and also, you know, the power plants that need to power all those GPUs and all that. But machine learning is about efficiency. You know, sure, like at this point, it feels like everyone just throw money into the problem until they go away. But at some point, money doesn't solve everything, maybe. So really, it's about how do you know, scale it. A lot of time, people would actually simplify, you know, the environment that they have. So for example, you're playing a video games. The most straightforward is to just feed whatever data the video game engine has produced to the models and have it to learn it. But after a while, you might go like a bunch of these observations doesn't actually give you any meaningful rewards. and so you're kind of trying to scale, simplify it down, or you might tackle your learning algorithms. So a lot of these algorithms has different trade-offs. They might be more efficient at doing one thing and not efficient at doing another things. Yeah, and also another problem that runs into reinforcement learning at the very start was that what are the practical implications for all of this? At the start, they were all just playing chess, playing Atari games, they were all just playing video games. Why? Because the people study them are bloody nerds and they only know how to play video games. There are problems that are obvious that you can use reinforcement learning to tackle them, and there are problems that you might not know that reinforcement learning would be good to tackle them until you try it out. So that is, I guess, a big challenge. Language model was one of them. Language model wasn't trained using reinforcement learning up until 2 years ago, I would say. I mean, to be fair, language model didn't really exist until 4 years ago. And that's one of the real, a good showcase of reinforcement learning, finding kind of problem that it can tackle. And I guess we can talk about a bit of practical applications. Something has 5 practical applications. One of them is robotic. So, when I was doing my master, robotic was all about writing control algorithms and writing, dynamic kind of models for all of these robots. I was doing crazy, bloody matrix multiplication because a lot of time, robot was still programmed by humans. You look at the car factories, you're like, oh, the robot are so cool, it's doing all of this action. An engineer spends 6 months programming it, and then maybe spend another 6 months trying and error, finding out hey, the shit I just programmed doesn't work. Now I have to hand program it. And for a car factory, it might be lifting a car from this to here. That is a very simple action a human can. And how do you program human hand to solve a Rubik's Cube? It's virtually impossible. And reinforcement learning kind of finds its groove. And in fact, this screenshot that I took was another OpenAI kind of showcase before they become post-AI and only release ChatGPT model and make a shit tons of money from investors. They were using a robot hand, this robot hands here, with no human program whatsoever, and having a camera looking at the hand, and then one hand solving Rubik's Cube. You can actually find that on YouTube. They still have that showcase. And I think it was back in 2019, right before they released GPT-3. That was the cool research that they were doing, and they were using the gym kind of library that I showed you. Obviously, there's a back end of the robot actually feeding information to the gym wrapper. But yeah, that was one big one. Navigation, so self-driving car. Everyone is doing that with reinforcement learning. All the Chinese car factories, they were crazy about it. Again, you can't hand program. They try to hand program all the scenario, but the roads are just crazy. I literally saw the news yesterday that someone in Chongqing, they were taking a self-driving car and someone took a ditch in the road and didn't put up sign and car just drove straight into the ditch. It was a huge ditch. I don't know how they can take a ditch so big in the middle of the road and whatnot. But yeah, that's the thing. It's a human can simply not program that. You cannot foresee someone dig a ditch in the middle of the road. You want your model to kind of learn that inherently. And the leader of that in this world is NVIDIA, because they build all the hardware for that. So they also want to build application for people to use their GPU. So NVIDIA have libraries. So it's called Isaac Sim and Isaac Lab. So Isaac Sim is kind of their way to do physics simulation using GPUs. So it's a whole suite of application that you can once you build kind of robots in your CAD program, you can import it into Isaac Sim and have all the control stuff. I think also have a Python wrapper, so you can write Python program. And Isaac Sim is kind of like, it's similar to the OpenAI Gym model. It's like the library on top of Isaac Sim that allows you to train and simulate literal robots in simulation to do things that you wanted to do. I haven't tried any of those because I don't have robots. I don't even have my own room to try a robot. So, but it's a really cool application that if anyone is interested, you can definitely go look into it. Maybe we can do a session. I don't know if anyone here is into robots or not. We can if we want to. Another one was gameplay. So reinforcement learning really kind of like earned its role in machine learning when Google DeepSeek put out AlphaGo that beat who is that Chinese Go player, that #1 top Go player in the world. It was 4-1. Like beforehand, Go program was really simple. If a master Go player want to improve, they would actually just read books and play against other players because it's so complicated. And that was kind of the first time that people realized that machines, because at the time machine learning model was it was your scikit-learns, your linear regressions, all of that. They were really good at extracting insight into data, or reducing kind of complex data into kind of simple data to present. But no one ever thought that they can exhibit complex behaviors. They thought that was impossible. I guess reinforcement learning kind of take off from that. And again, the next stage was having language model to kind of learn not just from all the text, right? They actually, well, there's still great debate into it, but there was actually a lot of people believe that language model have emerging behaviors through reinforcement learning, through simply, having the model talking, and then if you build appropriate rewards from it, a lot of times the rewards are just another language models, grading what this language model is doing, and then through that, emerging behaviors occurred. That's what a lot of people believe that DeepSeek was able to achieve, because DeepSeek R1 was, they basically built on the previous DeepSeek, which is DeepSeek V3. Very capable model, but not mind-blowing. But after whatever they released, they actually released a lot of the method of how they achieve all this training that I've done. And they were all of these behaviors, we don't see any of them in the data set. We didn't program them into our fine-tunings. It was all something that the model kind of learned themselves. That's what they claim. So reinforcement learning will likely to become the kind of, well, not will likely, it's already is kind of the next frontiers in a way for language model to exhibit even more complex behaviors. And if anyone want to kind of get into it, so Unsloth, so super, all of this shit are complicated, but smart people have built library that already do that, just I didn't build all those complicated reinforcement learning algorithms. You just use stable baseline. If you want to fine-tune your own language model using reinforcement learning, Unsloth is a really good library that do that. If you go through their documentation, they kind of teach you how to write a good reward models. Not to teach you how to write a good reward, just how to teach you how to write a function that would be useful to use their library to train. And they also pride themselves on being able to run this in consumer kind of hardware. So a lot of their training, they showed the one that they showcased. They were training 1 billion parameters, to do what DeepSeek was doing. They were doing that on a RTX 3090 or something like that. Obviously, it took them 200 hours or whatever. But yeah, so that's another one. So if anyone's interested, we can look into that later on. Yeah, that kind of conclude my presentation. So really, I just talk a bunch of shit about what are the basic concept with reinforcement learning, and talk about a bunch of shit of what are the learning algorithms that nobody understood because no one understood how scikit learns. If you have model.learn, you use model.learn. Don't write your own algorithms. But really, if what you're doing is kind of novel, you really have to dig deep into how the behind the scene works, and you also need to experiment with how established algorithms. There's no one key to fit them all in kind of this field yet. So if you're doing something new with your data, it's good to first of all understand how they works and also experiment with what you have, so you can find what is useful for you. Also talk about a bunch of shit, the challenges and all that. Yeah, and I guess that's concluded. And if anyone is interested with I kind of have not an actual problem, it's not an actual problem, but it's a hypothetical problem that I hallucinated myself and then I implement kind of all the application that I have. You guys can go through my GitHub page. All of this is really just showing you how to use it. It's really showing me how to use it because I often forget, I would write a helper function, I'll forget how to use it 2 days later. This is for myself. But if you were wondering, well, how do I use it to train well, not train, but how do I sample all the models? You can go through it here, and you can just go into the function. I got ChatGPT to write me a bunch of comments. I was write a bunch of comments for this. If you don't understand, you can go through the comments. If you still don't understand, you can talk to me. But I guess if you want to learn, and if you have a problem that you think is good, the most straightforward way is actually just trying to implement it. Trying to obviously do a bit more reading regarding this topic first, but then afterward actually just throw yourself into it, and then then you will discover what you know and what you don't know. Yeah. I guess that's conclude everything. Anyone got questions? Am I going to do more with the solo project? Probably, because I can probably, I've already synced 6 months into it. I feel like the shit that I was doing was already, at least 2 months worth of PhD work. So if I were to do a PhD, I can that would be 1 or 2 months worth of work, and I did that in 6 months. It's still very primitive. And to actually pass what's the first thing that you pass in PhD? The confirmation? Yeah, the confirmation, the first confirmation, that will probably not be enough. I probably have to do a lot more experiments with the things that I have. I need to find more data. So the data that I have wasn't very, they were very old data. They were from 2010s, so they weren't very up to date. So I'll probably need to find better data to experiment with. But yeah, in terms of the basic, I kind of already built the basic. To build on top of that with actually doing the research bit where finding out does the algorithm actually works? What hyperparameters would this algorithm works with? That would probably be the next step. Whether I have time to do it, I don't really know. Yeah. I mean, I still have a full-time job. It looks like I don't, but I do. Yeah.
I want to ask about the decision transformer. Do they use attention mechanism? So
the decision transformer, I can actually find the paper right now. So Hugging Face actually have a very good page called Hugging Face paper, where they have a bunch of Is it this one? Oh yeah, there you go. Oh no, wait, this is not it. Maybe I have to go find the GitHub page. Maybe it's this one. Oh no, there you go, the official code base. Oh wow, they only have this. Maybe I have to go to the paper, but in the paper, they talk about using the existing kind of like data, because with OpenAI Gym, not only the interaction, like those interactions, they also, all those sample environment that you saw, they also have a bunch of data, like people trying out different algorithms on it. So there's already a bunch of existing data on the transformer. So what they do is that they just took all those data, feed this through this transformer, and then it's basically a mini ChatGPT. It's like, so if you look at their code, they recreate the transformer architecture with slimmed down parameters, and then they were able to exhibit better better behavior. They were able to achieve better outcome using this architecture. And they didn't do any reinforcement learning trainings. All they do is took a bunch of data from other people that have done the training and the interaction. So obviously they were training on really high quality data. So they were also talking about one of the success they contribute to is that there was already successful algorithm implemented in this environment that exhibit optimal behaviors. They took all of that, they took a bunch of all of that, and just trained it through, they do a pass-through of this, and this model also exhibit those behaviors. So what they would exhibit even better behaviors. So what they hypothesizing that just like a language model, this was able to pick up traces of the behaviors, connect the dots between different behaviors and form new behaviors. And but they contribute that to already having existing behaviors, data that are good, that are already producing good reward. So this is it's kind of throwing a language model into that. And in fact, you can probably I've seen people using existing language model that are open weight and throw them into completely unrelated environments with a bunch of interaction data already, and then having that model just simply acting as you are a this. Now you see this environment, produce this result, use that as a chat template, and then the language model were able to produce that sort of behaviors after some fine tunings.
So decision transformer is not only for large language models.
So decision transformer is then adapting the architecture of a language model to this specific problem. So when they were training it, there was no pre-training using large language model. They were training this from scratch. They were doing supervised. They were doing it's basically pre-training in language models term on a bunch of existing high-quality interaction data from all of this environment interactions. And then they throw it, after they trained it, they just did what I did before, they throw it into the environment, they ask it to, they look at the observation and then they produce an action from it, and then they feed that action back into the environment, and from that they can go ooh, wow, this model didn't train at all with the environment, didn't do any online reinforcement learning, none of those complicated policy gradient shit. They were just doing normal, backward propagation on existing high-quality data, and they were able to produce, good results using the transformer architecture models. Yeah. So the word decision is just whatever they throw into it, because this model is making a decision. Yeah. I wonder does the paper actually have better detail on this? Field PDF. Free PDF things. Yeah, they were kind of this is what they were hypothesizing. They were saying that, imagine this is like a search problems in here, right? And here's the goal. And then they were like, oh, we have a bunch of like training data from a random walks, just from, it's do a bunch of this. And then they were saying their model was able to figure it out without, doing any, reinforcement learning on this like graph, like walking graph. They were able to just like deduct like, the best possible outcome based on the random walk data sets that they have. Yeah, and they also have an algorithm. This is like, this is basically kind of what I was showing. And yeah, and they were able to see that like, their models was good, not just better than, other learning methods, while some learning method was almost as good as it. And they were doing a bunch of, well, there's not much graphs in here.
So they're using the LLM architecture to apply the problems not native to LLMs.
Yeah, you can say like that. They basically look at reinforcement learning. They were like, well, hang on, like we can treat that as a sequence-to-sequence modeling. And then they were like, if we have enough data of how all of this interacts in a sequence-to-sequence manners, can we train a model based on all of this data and exhibit better exhibit behavior that return better rewards. And I think they were able to show that, were they? Yeah, so it says that in some scenario, they were prompting the models for higher returns than what's available in the data set. And in some cases, it can sometimes capable of extrapolations. So yeah, so they're saying that like in some scenarios, this is a good way to model what they're doing. So I think Pong was one of them. Now Pong wasn't, so you can see that like in here, the best trajectories was somewhere over here, and they were not able to ask, the model to produce better reward than whatever the data has. But in other cases, I think it was this one here, in this problems, they were able to, so first of all, the model was always better than whatever the I guess example data that they have, and the trajectory's best reward is only in this here, and further prompting it produced even better results. But in other cases, it wasn't. Like you look at this one here, Walker is the like two-legged walking things over there. It has a drop-off after a while. And Hopper, it was basically one-to-one. So yeah, it's like a hit and miss. Like in this one here, it was not able to produce any better results than whatever the trajectory already has. It was kind of just hovering around what the trajectory was able to have. So, yeah. So was there other question? Where do I usually find the library? I mean, the things about, so this is not really frontier research in a way. So let's say if you want to, there's already a lot of people with shit tons of money throwing money at this problem. So a lot of people would have already rolled up useful library to use. So if you want to do reinforcement learning, well actually no, but Hugging Face is actually a really good company, also resources for these sort of like new machine learning stuff. So Hugging Face courses. So you can see that Hugging Face already have a bunch of like courses that, you know, if you want to learn about it, they would have. Obviously, it's using their libraries. So if you look at the LLM course, you know, they talk about a bunch of like, what is language model and what is like transformers. And then it just showed you like, here, like, you know, here's what transformer is and here's our implementation of how to use transformers. Obviously, there's a bit of like promotion going on, but at the same time, like, you know, they have really good resources in terms of like, you know, these sort of like new emerging machine learning stuff. So they have one on diffusion. So if you like, you know, want to see how kind of diffusion model works and how do they produce like crazy good image results, like this is one. And they also tells you like, hey, you should use our library to deploy diffusion model. And they also have a reinforcement learning, and it kind of just all the stuff that I was talking about, but even deeper. So they talk about gradient, policy gradients. Kind of like see some of the slides, I stole it from them. They also have, you know, so all the math that they walk through it. They also have quizzes. Yeah, so they got pretty good stuff, so if you want to explore it, they should definitely be the place to do it. And they also have like a bunch of like Jupyter notebooks that you can use. So you can just straight up see like how do they so they got a Jupyter notebook in Google Colab, so you can see like, oh, how can you do embedding? How do you do RAG? So some of the RAG stuff. So now they integrate a LangChain. Like, you know, do you want to like, yeah. So Hugging Face is a really resource-rich website, I would say. And you can also pay them. They also have inference points. You can pay to use their inference. You can pay their host model. So all the open weight model is on here. If you want to use it, it's like, for example, the new OpenAI model. Like, how do you want to use this? You can just use their library. If you have a good enough computers, you can use their libraries. They also have a way to deploy, so you can use their inference providers. They also have a like library, so if you click into it, they already have a bunch of setup, so you just copy their setup and then you go to your cloud provider and throw it into it, and then they will already spin up whatever containers that you need. So yeah, Hugging Face is really the way to go. Seems like I'm only using Colab. Partly, yes. So if you look at here, so all of my kind of like back library, I write them in Python. And then I use Google Colab to like test run them, because like with Colab, or like not Google Colab, I host it on my own computers. I use Jupyter Notebook, so I can just like yeah, so here if I want to like test run the function that I use, so for example, like I wrote like a helper function that helped me to transform data. I just test run them in Jupyter Notebook, and if I need to change something, I would normally have to change it in the Python code, refresh it, and run it again in the notebook. Yeah. And another reason is because I use like Docker containers. So if I want to like run it in like a normal environment, I find it easiest to just like host kind of like the Jupyter Notebook environment in my container environment. I don't have to install any dependency or anything. I just spin up the Docker containers. I don't even have Python installed on my host machine. I kind of like do all my Python developments with Docker containers now. They're a bit of a pain in the ass to set up, but once you like know how to set them up, you can set them up throughout different kind of you can set them up throughout different kind of like computers as well. So like I don't have to go set up the new like Python environment again in this computer. I just get the images, or I just like pull this GitHub repositories, and then if they have Docker install on it, I just run Dockers, and then that's that.
Maybe in future, in the next Meetup, Victor can teach us how to use the Dockers, the practical tips.
I just know the 3 tricks to use Dockers. Like most of the time, I just look at people and now I don't even write my own Docker files. I just get ChatGPT. It's like, I want to do this. Write me the Docker container. Write me the Docker files. Write me the Docker compose. I need to spit it out, and it just spit it straight out. It's like, it's really good.
For Colab, you cannot deploy it if you don't
No, so Collab is their own, they already run their own containers. So you run in their environment. But the things about Google, like Colab, is that, wow, you kind of have to reinstall all the dependencies.
What other choice than Colab, like the cloud service? Maybe Sean is interested in
I don't really use other cloud providers because I have a good enough computers, so I haven't run into where I need to use cloud. Someone just say Ripit is good. Honestly, I just use Amazon. I just use AWS. AWS have a lot of resources into it. Learning AWS is probably useful. I don't know how useful it is in Macau. I haven't seen anyone sell AWS here yet. Does any of you use AWS at work?
Not yet. Probably not in the near future. But
I mean, in Macau, it's probably more useful if you use Alibaba Cloud or something like that. So yeah, I don't really dabble into, because another thing is I'm not an infrastructure engineer. I don't even do this for my fucking day jobs. So I don't really see a point for me learning how to deploy cloud.
yeah, I feel good tips on using Docker would be very good. Showcase a few demos.
Do you guys have you must have IT department that deploy Dockers? Yeah, so maybe get them to come and talk about using Dockers. Yeah. Because Docker is the lowest level for deployment. And then the next thing is all right, now you have Docker, you want to deploy not one Dockers, you want to deploy a bunch of Dockers, and then you start getting into doing Kubernetes and shit like that, and then and eventually you'll be oh my god, all my Docker swarms is not good enough anymore. It's never ending. But it's I feel in terms of doing data stuff, I feel using simple Docker is good enough. Because the things are once you go to the cloud or a private server, your IT would have scalability built into mind. So let's say if your problem need 190 cores CPU to crack, just throw them and then have them to have the infrastructure people to figure it out. Just my Python code would need fucking 120 thread to run. You just give me 120 thread. Yeah, who's the mystery guest? Yeah, who's the one who raised the questions? Cool. Yeah, I would get a question. Would you guys see, having reinforcement learning used in any of your day-to-day job? I don't imagine that would be useful. Because if you're doing data analysis, it's not something that you do
It looks like you use reinforcement learning on some complex system, like robots, cars, and you name it.
So if you have a decision to make, I think it will be a good, like, you know, if you guys have a decision chain, so let's say you base on this data, you know, you have to make immediate decisions. I don't know what that would be. Maybe like, you know, deploy like 10 tables or like use 5 tables. I don't know how casino works, but like, yeah, that could be a useful like way to do it if you. Back in the day, reinforcement learning are called dynamic control, stochastic dynamic control programming. That was like before they have our fancy words for it, because that's kind of what it's doing. It's like it's doing control problems. I don't know whether any of you guys have done control problems, but like, yeah, it's like really about, you know, how do you do dynamics, and then like they were like, are we too lazy to do like a bunch of Laplace transforms? Like, you know, let's just have like a simple like iteration to update that. Yeah. Cool. That's no more problem. I guess it's time for lunch.